Hello everyone, my name is Kurghinyan, and today I'll be presenting my capstone, Detachable Leg Joints for a Quadruped Robot, a concept of operations. My supervisor is Suren Atayan, who unfortunately did not make it today due to illness. My advisors are Vahagan Zargaryan, Khachik Grigoryan, and Sarkis Zeytunyan. So, as an introduction, robotics has developed quite a lot in the last 3 or so decades, and some of the highest performance examples you can see on the screen at the moment. And our company, Cyberfusion, works on robotic development here in Armenia as well. The goal is to democratize robotics and make it more available to students and researchers. It is done through these 4 tenets that you can see in front of you. And again, the goal is to make it available to everyone, much like personal computing is today. How computers transitioned from being very specialized and expensive tools to modern commodities. And the robot you can see in front of you is our first robot, Eig. And you can see some examples of some field tests that we have done very recently. All of the development as part of this capstone was done with Eig as its base. So throughout the development process, we noticed that the partial disassembly is very often required of the robot, and it was especially apparent due to the sequential design of its various components, which made it extremely time-consuming. It was especially noticeable in the leg. From here, the idea to make the leg detachable came. The advantages of the detachable joint would be, obviously, the first thing would be the divided assembly. If you can assemble the leg separately and the body separately and just click the 2 of them together, that just makes it much more reliable in terms of time. More people can work on the robot at the same time, speeding up the process significantly. It also makes it cheaper to maintain if the robot is damaged, which in case of quadruped robots, the parts that get damaged the most are the legs. You can just replace the leg, not the entire thing itself. You don't have to necessarily, depending if the joint is designed simple enough, the user might not even be required to take it to a specialized facility to be repaired. And of course, it also adds some modularity to the robot, namely that, for example, all of the legs can be disassembled, and they can be replaced with wheels, for example, which, depending on the use case scenario, might be advantageous. So some related work regarding modularity and detachable joints. The word detachable has not been necessarily used in this context, but modularity has been quite a prevalent topic. The 3 examples you can see here all take the leg as a base unit for a robot and then make the robot out of it. In all 3 cases, they use connecting ports and specialized kind of like holes that were pre-made to include nut and bolt joints to make the leg easy to detach and replace. Another big advantage that was brought to the robotic stage was by the developers of Animal, which introduced kind of the idea of modularity in the sense that the robot's leg should be developed similar to a robotic hand actuator. All 12 of the joints of the Animal and the Mini Cheetah and the Unitree Go 2, which were kind of inspired from this design, use the exact same actuator, making it much more easy to replace components. In case of the Animal, unlike the other 2, all of the legs are made to spin 360 degrees. The disadvantage of this is that the actuator that controls the knee would have to be mounted at the knee joint, which would increase the inertia of the leg, making the other 2 actuators controlling the leg a bit difficult. This was kind of changed in majority of the modern day robots, such as Spot, the Unitree Go 2, or most Unitree designs, and the Cheetah and the Mini Cheetah. So to summarize, all of these, in general, modularity is not a new idea, and all of them use screws, bolts, and nuts or tapped holes to get the modularity out of it. The potential downsides of this is that it requires a tool to operate, so it does not work on its own. Without a tool, the joint or the robot itself is pretty much non-existent in terms of its modularity. There's a possibility of losing a component in the field, especially when doing field works, that the small nut can go loose in the grass, and suddenly the robot is completely useless. And depending on the urgency of the situation, for example, search and rescue operations or in military scenarios, taking time to unscrew and screw back 6 separate joints may be time consuming. So some assumptions that have been put forth for the development of the detachable joint is that it shouldn't impact the robot's normal operation. It is able to withstand expected loads. It is simple enough to install and operate. It cannot be accidentally unlocked. It is not significantly heavier than the original joint. It is not fragile and can withstand moderate user abuse. And the design is independent of the actuator. So for the Ike robot and most commercially available robots as well, such as Spot, there are 4 main sub-assemblies, which is the body, the hip, the thigh, and the shank. And there are 3 joints joining these 3 sub-assemblies together, which is the hip abduction adduction between the body and the hip flexion extension between the hip and the thigh, and the knee flexion extension between the thigh and the shank. The reason that the HFE was chosen to be made detachable first is, unlike the other 2 components, it is located in the middle of the 4 sub-assemblies, providing the greatest amount of modularity to it. And this was also the main area where often replacements have been done throughout our development. And the KFE has quite complicated kind of structure due to the power transmissions required. As you can see, unlike the animal, our actuator for that controls the KFE is located at the hip to lower the leg inertia. And the hip abduction adduction is a relatively simple joint, which, although made detachable, the entirety of the leg would come off rather than part of it, which would partially defeat the purpose of making it detachable and easier to assemble. Most of the sequential assembly is really concerned with the leg. So for the Envision system, I was advised to build on top of the existing joint, which you can see on the screen right now, and kind of subdividing the joint into 2 brings forth the following issues that need to be tackled, which is torque transmission, secure coupling, and a fast lock and unlock mechanism. We'll tackle the torque transmission first. The initial idea was to use a keyed joint, but the issue with this is because of the short length of the shaft, the key would have to be press fit, and that would completely remove the entire idea of making the leg detachable. It might as well be a single piece. So the idea was changed to use dowel pins. We will be using 3 identical dowel pins made of hardened steel. These are dowel pins that are also compatible with the actuator. The actuators that we use in the robot are already have pre-drilled holes for the dowel pins. And because they do, the initial idea was to place them on the actuator themselves. However, the issue with this is that the pins are at a smaller radius, which means they can transfer less torque, and they also were placed symmetrically. So there is a possibility of assembling the joint incorrectly and then realizing it, having to detach it and reattach it, and that takes time. So for the second configuration, we added 3 additional pins on the stator module that connects to the stator module, which is the bigger one. And the reason being that we have available space to work with. We can place the dowel pins on a larger radius, allowing to transfer more torque, and we can place them asymmetrically, which removes the possibility of assembling the joint incorrectly. The most important part in transferring torque is to calculate the shear stress. The dowel pins need to be able to withstand the shear stresses that arise during the operation of the joint to be able to function. The formula you can see right there, it is shear stress is force over area. In this case, we're concerned with torques, so it would be torque over the radius. And because the cross-sectional area of the dowel pin is a circle, there you can see the formula. For the worst case scenario for a single dowel pin, we have we place them at 2 different radii. Other than that, the torque transferred and the dowel pin diameter remain the same in both cases, obviously. And for the worst case scenario, we achieve the highest amount of torque or highest amount of shear stress of 318.5 megapascals at the smaller radius, and 193.7 megapascals at the larger radius. Because we're using 3 dowel pins, these numbers would be divided into 3, making it 106.2 megapascals and 64.5 megapascals. The dowel pins are pre-purchased components, and although the manufacturer doesn't provide us with the shear stress of the specific material that is being used, it is judged to be approximately 375 megapascals, making the dowel pins a correct use case scenario. So for the coupling and locking, which are intrinsically related to each other, the first idea was to use a pin joint. In this case, the pin kind of acts similar to a door key. It has asymmetric cutouts. It kind of slides in, gets rotated 180 degrees, and locks the components together. And the body of the pin entirely keeps the two components from disassembling from each other. In this first kind of early design, the accidental unlocking of the joint was a flaw, so that was upgraded or improved with a groove as well as a catch pin to catch it go into the groove, and a spring lock was added to make sure that the joint doesn't disassemble itself. A major issue with this type of design in general is that there is quite a lot of wobble that is possible in the joint, and tolerancing would be very important, and several, if not 5 or 6 iterations of the joint would need to be done so that the components are machined as precisely as possible to not allow for any kind of wobble, which would be extremely significant in terms of the impacting the operation. The other issue is that the pin would need to be lubricated, being made of steel and the other components being made of aluminum to slide easily. Because the pin is completely removed from this kind of a joint, lubrication is not necessarily a good thing, because the pin itself can stain itself. The lubrication the grease can get worn off, or it might stain the user, especially when used commercially. So these were some of the major issues that were found. Another idea to make the joint detachable was to use a slam latch, so that it would be using a spring-loaded cam. One component would slide in, the latch would kind of retract back and then go back into a pre-drilled hole holding the two components together. In this case, the handles, which you can see at the kind of top part of the diagram, those would act as actuators. There were some issues with this regarding some manufacturing. Some of the components were a bit too thin, and a couple of the design was partially changed. The latch was divided into 2, and this did allow for easier assembly, but still there was an issue with the components, all of the components being very complex to manufacture, and because of the number of moving parts, all of them introduce potential areas of failure. So with these two initial ideas kind of out of the scope, a third idea was decided on, which was the one that was built, and I will demonstrate it shortly. It was to use a screw joint. In the earlier design, we used cap screws as the basis of the spring. Those are hollow type cap screws, but the longer type cap screws already are made to hold two components together against each other, such as a rotating shaft and kind of a bore or a housing component around it. This allowed for much easier manufacturing and lower complexity. There are less moving parts, which make it less prone to failure. Obvious disadvantages would be that it still requires a key or tool or screwdriver to be used, and it is much slower than the other two possible solutions, which is why initially this was not considered. So to verify what has been built, all of the earlier assumptions have been maintained or achieved, rather. In terms of the weight of the joint, it is almost twice heavier than the original connector. However, this is still within allowable limits, because when kind of put in the context of almost 900 grams per actuator, so the two actuators, each of which are being connected through this joint, are 900 grams each, while the component itself is short of 180. So this was still negligible enough to be considered good. Some limitations of the solution and throughout the work that has been done is obviously the use of screwed components. It requires a tool. much like other versions, kind of as that I discussed in the related work. There's a possibility that the hex socket in the screw joint can be round off, or in Armenian sarvatelni, and that means that the joint might become completely useless. So kind of careful use is advised, and maybe periodic replacement of components may be needed. And it's obviously not as fast as originally envisioned, which is why the screw joint was not initially considered. The issues that have come with the pin joint and the slam latch was mainly due to the ineffective time allocation, but they are still worthwhile solutions and can be researched further. Another next step would be to design the HAA and the KFE joint to be also made detachable, increasing the modularity of the robot. The amount of testing that has been done with this joint has been relatively limited, again due to ineffective time allocation, but a good, useful next step would be to do some finite element analysis as well as field testing to validate the results that have been achieved. And finally, the integration of the electrical interface would be an important kind of next step, so that the wires that attach the two actuators together don't have to be detached separately. It's all included in one joint. And now let me really quickly demonstrate how the joint works. So this is the only joint that has been made detachable. This is the only one, and with just a couple of screw movements, the entire joint comes together. This is what I meant when I was referring to the electrical interface. The wires need to be separated on their own in this version, but at a later kind of design can allow for them to be integrated as well. Now, I can't, for example, connect it in any way except for the one possible way, which is for the asymmetrical kind of design and placement of the dowels. Before I finish, I want to make some acknowledgments. First of all, to my supervisor, who introduced me to the robot itself, welcomed me to the Cyberfusion team, and allowed me to work on this. My advisors, Vagan Sarkyan and Khachi Grikoyan, who were always very, very ready to provide feedback and assessments. To my professors, Sarki Zaytunan and Levos Tepinan, to even introducing me to computer-aided design and kind of opening up the world of engineering design for me. And finally, to Mariam Mukrachan for kind of her non-stop timely technical responses and issues and feedback. Thank you very much, and all of the questions are welcome.
Yeah, very impressive work. You gone through many iterations, through mistakes and corrections. Can you switch it on?
Come again?
Can you switch it on?
Unfortunately, I cannot, because the only one joint is replaced to be detachable, and that kind of, as you noticed, the initial connector was much thinner, and the detachable joint is a bit wider. And the reason that I can't turn it on, which I can turn it on, however, it will definitely start flailing around and probably damage somebody or something, because the reinforcement learning, it wasn't taught using the kind of wider detachable joint. This is a relatively new thing, while the training of the robot and it's being able to walk has been in works for almost a year now.
So you rendered it useless.
Well, until
that's
yes, until the other ones are replaced.
It has very good potential. If you make all joints detachable, it will make maintenance much easier, as you envisaged. But you still make use of a tool, which was one of your stated goals, to get rid of the tools and get rid of the screwing and unscrewing. But I saw that the manual work is very small, which is very good. But in the dark, you may need headlamp or something.
That's true. That is very true. That is very true. Yes.
Or you make your hex screws fluorescent.
I guess depending on the use case, and depending on because the robot is made to be kind of an open development platform. Depending on the use case, those kind of more specific additions can definitely be made, but in the future. But those are good
Yes,
notes.
my comment is very good word.
Yes, thank you.
I have a couple of questions.
Yes.
A very good engineering work, Daniel. I always welcome real life projects that topics that come from industry and are done as a student capstones or research projects. And I see that you included some real commercial elements, and I am glad you used Ulrich's book I gave to you, Design Specifications. Can you go to slide number 6? And these are some design requirements, list
Yes.
design requirements. So I understand that it's very difficult to satisfy all of them as a student project, okay? And in slide number 15, you said that these requirements are verified. So how did you address these requirements in your project? For example, so you mentioned in your requirements dropping and bumping.
Yes.
So did you verify that?
I did end up verifying it during the assembly of the joint as well. On 2 occasions, I needed to completely disassemble it, including the dowel pins. And because the dowel pins were made with kind of negative tolerance, they were very tightly connected to the rotor to one of the actuators. And of course, kind of like prying it open took a bit of manual work. And a couple of times kind of the component was dropped on the ground, etc., etc. So that in of itself, the assembly process of it as I was kind of let's say fiddling with the component, kind of showed on its own that it is made to be sturdy enough for at least some abuse.
Okay, good.
I have a great yes. It's really great work. I also like it, and I would agree with the comments. Um, First question: how long does it take? It's a big amount of work I can see in that. What was your team? I think you didn't do this all alone, right? And how was the distribution of the work in your team? And the last question is, how much AI is involved and in what portions, like how AI has helped you? And have you done any material learning of like what materials would work the best?
Let me tackle those questions one by one. So, in our team at the moment, from the mechanical engineering side of things, I'm the only person. So the work in terms of designing the component was done by me. In terms of assembling the robot, the team was definitely involved. I was helped a lot when, I don't know, the robot need to be held up or several components need to be just screwed on, etc., etc. So in those aspects, I am very thankful to having had extra pair of hands to help me out. My supervisor especially was always kind of around and helping me out. Um, in terms of AI, the very little AI use was used during research. So to find similar robots that have focused on modularity, for example. Otherwise, AI has been used relatively little. Again, mostly for research purposes. For example, one of the robots that we were reviewing had used dowel pins, and we asked kind of AI to give us a summary of what are dowel pins useful, or provide us with sources which I could then go and read to understand the use of dowel pins. And in the same kind of regard, in terms of mechanical design, my advisors also helped me out, kind of giving me correct directions, and their experience helped me out as well. And the last question was regarding materials. I have done some material research. However, everything kind of boiled down to using steel for all of the smaller components because they need to be hard enough to take on or tolerate the loads that are generated. And the other component which is used, which is aluminum, 6065 aluminum more specifically, that's made more so because it is the easiest available and easiest to manufacture. The components, well, are designed by our team. They are not manufactured. Most of them are not manufactured here. The quotes kind of are sent abroad, and then the components are sent back. And for that reason, it was really not a question of which material fits best for this, but rather which material is available for us to continuously use.
Yeah. Got it. Thank you.
You said about the democratization of the
Yes.
robotics. What is your vision there?
The vision is that robotics are kind of like an obvious next step that humanity in general is going to. So making it accessible to as many people as possible is really the kind of the vision there. Similar to how cars have become like very available to everyone, or similar how computers have become very available to everyone. We see that the robotics is kind of like the next step of the next kind of tool that is going to be available for everyone. And that's kind of the vision that we are aspiring to. One of the examples being the Ike robot, which is kind of an open development platform. The goal is to make it the last point that I had. Let me go back. The multi-level programmability. That's really kind of one of the main ways that we're going to make it kind of more democratic. The idea is that you can take out the robot from the box, turn it on, and it will walk. However, if you are a researcher in a lab and need to do a very specific kind of work and research, and you know what you're doing in terms of programming, you can get up to the most basic levels or the most fundamental levels that it is programmed. And then again, on the other side of things are students which need to kind of slowly start learning, and for them they don't really require kind of in-depth level access to the way that the robot functions. They just need the robot to function.
I have two questions. One, is this the end of project, or you plan to continue and complete the work?
We plan to continue developing the joint with kind of more time in our hands, more availability as well. As I mentioned in the future works, the pin joint and the slam latch would also be considered as still viable to be implemented.
Okay, so you will still collaborate with your supervisor?
Yes, yes. I'm still part of the Cyberfusion team, so
That's great. And also, it's a good proof of concept. How much you learn from existing works, from other researchers, from other projects? When I look at your reference list, there are several online like blogs or website and those. So I want to understand how other works help you to move forward to this design.
yes. So as you mentioned, some of the online blogs was the reason being that mechanical engineering seems to be much more kind of experience-based design, and because of that, online blogs are kind of a bit more prevalent. But some of the more general methods that were used in the design, which are very difficult to kind of to cite, because it wasn't just one specific thing. It was a way of designing. A lot of it has been through collaboration with my advisors. They have helped a lot with their experience. Kind of online resources have also helped me narrow down certain focus. So for example, what kind of a component is much better, or even what kind of a component even exists that I wasn't aware of. That's really the main kind of area that online resources have helped me out a lot.
Great. Okay.
Thank you.
Daniel, quick question. You started by telling us the advantages of modularity or detachability, detached leg, then modularity. And then you had someplace what felt to me to be a acknowledgement of some disadvantages, like maybe why this hasn't been done before. But I was curious, unless I missed something, in the disadvantages, is there anything about the actual I don't know, design, assembly, sort of sensors, wiring, maybe stiffness, or I mean, is there a added challenge or some kind of trade-off when
Modularity.
introducing modularity, but do you sacrifice something compared to conventional design?
I have unfortunately not been able to find any kind of specific mention in other kind of papers that have also developed quadruped robots. So I can't really say that anybody has mentioned that there is some kind of a trade-off. There is obviously a trade-off, for example, the weight, which is relatively important in case of quadruped robots. The other trade-off is that you are dividing a single component into several, and by that fact itself, it is potentially less durable. So that's one other trade-off. Really, those are kind of the main areas. Depending on if there are any specific design constraints for the specific quadruped that someone is developing, having the thigh kind of be located at a further at a distance further from the center of gravity might also be a potential trade-off. But those are all something that has come up throughout the design process. I've unfortunately not been able to find any mention of it in other papers, partially because especially the more commercially available robots like Spot and the Unitree, they don't have paperwork. They have very little kind of academic work that is published, that is available. So however they have achieved their kind of design goals remains a mystery. It's kept within their company.
Yeah, I think that's a good answer. Although I think you answered it also implicitly yourself. So if you're putting more weight distally, if you're putting more, I mean, that's going to affect control, stability. That might be interesting to acknowledge for future work.
Yes.
For others, or for if you're particular.
Related to the very first question that was answered, which is why I can't turn it on right now, is because one of the joints is kind of like set apart. And even if I were to replace all four of the joints, I would still not be able to turn it on because the model has been trained using the older type of joint. So it's really, in this case, it's really a matter of time for the kind of the new version to be trained on the kind of new type of joint so that it is able to work or walk.
Thank you.
A small question regarding the versions that didn't make to the panel car. At what point did you decide that this is not going to work and I need to work on another design? So how did you build it and test it and it didn't work in program?
The goal for this semester was to build and test them. However, that was not done. All of the work has been kind of all the types of joints that have been eliminated within the design process rather than the building process. Partially because it would take a lot of it would take a significant amount of time to kind of like go back and forth with where we are outsourcing the manufacturing of it. And the second issue being that although these designs were kind of work in progress, after talking with my advisors and kind of like going into an in-depth review of both of the designs, they still mentioned that there are a lot of uncertainties with the design. There are a lot of things that still need to be improved. So from just judging from their experience, they advised me to just not go forward with them because it would be a waste of time. Yep. All right. Thank you very much.